In this video, we'll do a few simple calculations regarding the Lunar Lander, Lunar Excursion Module, the LEM lander. So, 50th anniversary of Apollo 11 landing on the moon today. So let's celebrate that with a few physics calculations. As I looked up some information about the Lunar Lander, this varied from mission to mission, but around 15,100 kilograms with the fuel on board, not used yet. And the descent engine had a maximum thrust of 45,000 newtons. As the Lunar Lander is starting its descent, getting out of orbit, deorbit burn, what kind of acceleration would the LEM feel, would the astronauts feel? Is this hazardous? So we can use F equals ma. As they're doing this burn to go out of orbit, kind of roughly they're horizontal to the moon's surface here. We do not need to include the effect of gravity of the moon here. We're just interested in the acceleration produced by this descent engine. So that's simple. F equals ma. 45,000 newtons of thrust, 15,100 kilograms of mass times the acceleration. You divide, you get about 3 meters per second squared. 3 meters per second squared. That's actually a little smaller than I thought it might be. This is just 1/3 of the acceleration of gravity on the Earth. So the astronauts would not be stressed by this. They did not need to sit in special seats to help manage the load on their bodies or anything. So that's manageable. So let's go a little further into the details here. The descent engine had a throttle on it with some control. If they wanted to not just use the maximum thrust, they could control at a level of 10% to 60% of the maximum thrust. And the LEM landed with about 10% of the descent fuel remaining. Different websites I went to had some arguments about this. The indicator on the panel showed less fuel left than this, but some people think that the indicator was a little pessimistic, that there was more fuel left than that. Fortunately, they did not run out of fuel. So what's the motion of the LEM if they're just using 10% thrust when the LEM is close to landing? Well, now we do need to account for the weight of the lunar lander. So I've adjusted the picture a little bit here so you can see my rough sketch. I like to make a rough sketch as I'm working problems. The LEM is here. We've got flame underneath it. We have mg downward. There's a weight on the lunar lander due to the moon's gravity. And then we have thrust going upward. I'm going to work the problem with the upward direction being positive. So the net force on the lunar lander is thrust upward, mg, the weight is downward. That's our net force equals mass times acceleration. What type of mass do we have? Well, I'm assuming that 10% of the fuel is remaining for the descent engine. Still has all its fuel for the ascent. That comes later when they blast off from the moon. So what type of fuel mass should we have here, and what's the total mass of the LEM? So 15,100 kilograms all loaded up. Fuel of 8,200 kilograms, and 90% of that is gone. So we're going to subtract that number from the beginning weight for the lunar lander. That leaves us with about 7,720 kilograms. And then a total guess, there are some maneuvering rockets on the LEM also that had a different fuel supply. And these were using up fuel as they got near the landing point. So I'm just guessing 7,600 kilograms is the number I'm going to use for the mass of the LEM just before it lands. I've reduced from 15,100 because we've used up fuel in the minutes of the descent, and fuel both for the main descent engine and for the maneuvering engines. So I'm adjusting the mass of the LEM system with this calculation on the right. Now I can come back to this calculation here. And interested, will 10% thrust do the job and help them land? So I put in 0.1, 10%, times the maximum thrust. Here's the mass of the LEM system now. Acceleration and gravity due to the moon, different than the Earth's. And then we have an equal sign that I didn't put in. I'll put it in now. Equals the mass of the LEM system times the acceleration. Sorry about it, got a little crowded there, but we've got the 10% of maximum thrust, the weight of the LEM, and then equals MA, 7,600 kilograms being the M. So you should pause and work this out on your own calculator. You're going to find a number on the left side here first, divide by 7,600. I came up with -1 meters per second squared. What's it mean that the number is negative? It means that the weight here is dominant. There's more force downward than thrust upward. So the astronauts did not do this. They did not come at the surface of the moon with only 10% of the thrust. This would be too fast of a downward acceleration. They did want the moon's gravity to win, bring them down to the surface, but they were going a little bit more throttling and they hovered sometimes. So it's just what would happen if the thrust was 10%. It's a hypothetical question. Well, let's go a little further here. What about hovering? They did want to kind of pause and pick a smooth landing area. What throttle setting, I used 10% up here, what throttle setting would allow the LEM to hover above the surface of the moon? Well, we've got some of these same numbers, but now the picture changes a little bit. When we're hovering, the acceleration number is 0. So we're going to have thrust minus weight equals 0 on the right side. We don't want the LEM accelerating up or down. We want to hover. So we've got the throttle setting. That's the unknown we want to calculate for. Maximum thrust, weight of the LEM, so our downward force, and then 7,600 kilograms times 0. That's going to disappear on the right side because it's multiplied by 0. So we have throttle times 45,000 equals 7,600 times 1.62 meters per second squared. This is acceleration of gravity for the moon, due to the moon. Multiply here, divide by this number, and you should do that in your own calculator. I came up with 0.27, so 27% of full throttle. The design of the LEM, they could vary between 10% and 60%. So this number is a reasonable number because the design of the LEM was to allow the astronauts to select some number in between 10% and 60%. Okay, a little further. Now they've been on the moon, collected rocks, took pictures, ready to come back to Earth with their items. And the ascent stage now is going to separate from the bottom part of the LEM. So we're going to have a different mass moving upward than we had before. So that mass with its fuel, 4,700 kilograms, and that engine has a thrust of 16,000 newtons. Why is there less newtons instead of 45,000? Well, they didn't need them. The fuel has been used up for the descent stage, and the descent stage stayed on the moon. It was kind of a launch pad for the Lunar Lander as it goes back up, and for the cabin carrying the astronauts and rocks. So what's the acceleration in this situation? Well, again, we're on the moon. The moon's weight creates a weight for the ascent stage. So we have to do this net force. Thrust upward, the weight downward gets a negative term, equals ma. Put in the thrust number, subtract off the weight, equals the 4,700 kilograms times the acceleration we're searching for. So on the left side, these two terms combine to be 83, 86 newtons. It is positive, it is upward. This thrust is greater than the weight of the ascent stage. divide by the 4,700, and I came up with 1.8 meters per second squared upward. Again, not a huge acceleration. The astronauts did not need special couches to sit in to help support their body in this situation. So there's perhaps some interesting things about the Lunar Lander. If you'd like to see some other physics and astronomy videos that I've posted, they're indexed, annotated at these two websites. There's no registration, it's free, but you'll find a list of the videos, a direct link to the YouTube to play the videos, how long they are in minutes. If you do enjoy the videos, please subscribe to my YouTube channel. When you're watching the video, click the subscribe button. And keep practicing calculations in physics and astronomy.